So for topic 13, we're going to be looking at quadratic functions. And in video 1, we're going to be looking at finding the axis of symmetry of a quadratic function and the vertex of a quadratic function. Quadratic functions have the form f of x equals ax squared plus bx plus c, where the a, the b, the c are just real numbers. A can't be 0 because if a were 0, we would have f of x equals bx plus c, which would be a linear function or linear model. We've already looked at those. The quadratic functions are built from quadratic expressions, which we've already looked at. Quadratic expressions in a single variable. We've already looked at quadratic equations in a single variable. So now we're kind of upping the game, and instead of having ax squared plus bx plus c equal to 0, we're letting a function of x be equal to ax squared plus bx plus c, where we recall that we can always replace the f of x with y if it makes things easier for us, although I'm probably going to push you to try to use function notation. And quadratic functions have some key features that we're going to want to be identifying. We're going to want to know how to identify the y-intercept, and if it's an application problem, we'll want to know how to interpret that intercept. We're going to want to be able to locate the x-intercepts if they exist, and in application problems, interpret those intercepts. We're going to want to be able to find the vertex of the quadratic function, and we note that a quadratic function is a mirror image of itself in a vertical line. That vertical line is the axis of symmetry, and we're going to want to be able to identify how to find that axis of symmetry. So for this first video topic, we're going to be looking at specifically finding the vertex of a quadratic function and the line of symmetry of a quadratic function. So kind of the first step in thinking about this is to think about quadratic equations that we looked at earlier this semester. We had functions of the, or equations of the form ax squared plus bx plus c equals 0, and we used completing the square on this equation to come up with the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And we want to recall in particular that this gave us the x values for which the quadratic equation was equal to 0. With a quadratic function, we kind of have this special case where when we set ax squared plus bx plus c equal to 0, we're just asking the question, when is the function equal to 0? When is the quadratic function equal to 0? We want to recognize in the quadratic equation that if we have everything over a denominator of 2a, that we can break this into individual pieces. Negative b over 2a and the square root of stuff over 2a. So with a quadratic function, we have a horizontal axis if the quadratic function is intersecting the x-axis. The quadratic equation right here just gives us the locations of the x-intercepts. So this x-intercept, the x value at this x-intercept is going to be the negative b over 2a, or the negative b plus the square root of the b squared minus 4ac all over the 2a. And this x value is going to be the negative b over 2a minus the square root of b squared minus 4a over 2a, or just negative b minus the square root of b squared minus 4ac all over 2a. And what we want to identify or notice is that we're adding or subtracting the same amount or the same quantity from negative b over 2a. So that means that negative b over 2a has to be halfway between these 2 points. So this x-coordinate right here, the x value right there, is the negative b over 2a, and the distance right here is actually just the plus the square root of b squared minus 4ac all over 2a, and the distance right here is also the distance b squared square root of b squared minus 4ac all over 2a being subtracted from the negative b over 2a. So that negative b over 2a, which is halfway between the two x-intercepts, happens to lie on the line of symmetry for the quadratic function. So this equation has to be x equals negative b over 2a. And to find the value of the vertex lies on the axis of symmetry, we would need to plug in negative b over 2a for the x coordinate, and the outputs would be the f of negative b over 2a. You plug that x coordinate into the function and get the output. So that's what this here summarizes. How do you find the axis of symmetry? Or, well, you take the negative b over 2a from the quadratic formula, and you understand or recognize that that has to give you the equation of the axis of symmetry, and then you plug the negative b over 2a into the function, so you get your x value, your input. F of the input gives you your output or your y value. You get your x and your y value, or the location of the vertex. Alright, so graphing a quadratic function by finding the vertex and the axis of symmetry. So again, we recognize that x equals negative b over 2a is the axis of symmetry. So in this case, we look at our quadratic function. We see that a is equal to negative 3/2. We see b is equal to 6. So I can replace the b and the a with the 6 and the negative 3/2. So we get x is going to equal the opposite of b divided by 2 times the negative 3/2. 2 divided by 2 is 1, so we get negative 6 over 1 times negative 3 is negative 3, which is 2. So our axis of symmetry is going to be at x equal to 2. So here's our axis of symmetry. So when we get the axis of symmetry, it's easy to get 2 points on the graph very quickly. In fact, what we can get is immediately is the y-intercept. So we want to remember that the y-intercept, the intersection with the y-axis, happens when x equals 0. So if we plug 0 into our quadratic function, we get negative 3/2 0 squared plus 6 times 0 minus 2, which simplifies to just negative 2. So we get the ordered pair input 0, output negative 2, input 0, output negative 2, input 0, output negative 2. And because this is the axis of symmetry, located the same distance from this axis but on the other side, there has to be a point that is the reflection of this point through this vertical axis of symmetry. So we get this point by symmetry. We get the point 4 and negative 2 by symmetry. And now all we need to do is locate the vertex, and we can kind of get a quick and dirty graph. Well, we know that the vertex will be on the axis of symmetry, which is x equal 2. So we just plug 2 into the function. We do f of 2 equals negative 3/2 times 2 squared plus 6 times 2 minus 2. So we get 2 squared is 4, divided by 2 is 2. 2 times negative 3 is a negative 6, plus a 12 minus a 2 is going to equal a 6 minus a 2 equals a 4. So the vertex is going to be located at the point 2, 4. So I go over 2, up 4, vertex located on the axis of symmetry. Now we can get a quick picture by drawing a downward opening parabola. And we can recognize that this parabola is going to be downward opening by recognizing that this x squared term means that this quadratic function is a member of the squaring family. This is the function family or toolbox function for all quadratic functions. And we know that the function family x squared opens up. And we know that to get it to open downwards, we need to reflect it over the x-axis, and we do that by adding a negation. So when we see that negative sign in front of it, we expect the parabola to be reflected downwards from our toolbox function topics that we went over. So this is a quick, dirty graph of the quadratic function using the vertex, the axis of symmetry, using the y-intercept, reflecting it in the axis of symmetry to get a second point. You want to notice that it doesn't give us the locations of the x-intercepts, and those are important points on the graph of a quadratic function. We'll look at finding those in video 2.